In the last video, we looked at being able to plot the relationship between two variables. Once we've got that sort of relationship, in this video now, we're going to look at how do we interpret that relationship. And is this correlation between two variables that we are seeing, is that necessarily causation or not? And correlation versus causation is one of the foremost sort of warnings of data science, warnings of statistics. Just because things are correlated doesn't mean one is causing the other. And we're going to take a deeper look into that. So first, let's look at correlation. These two graphs, two different types of height and weight relationships here, these two graphs actually have the same correlation strength. So correlation strength doesn't mean the steepness of that correlation. So here you can see one is quite steep and one's a lot less steep. But strength doesn't mean steepness. Steepness actually means not a lot because that's all to do with the scale of the variables you're looking at. Correlation strength actually means how much of the variation of one is explained by the other. So let's have a look at an example of weak correlation. An example of weak correlation would be it follows a kind of slope roughly, but within that rough slope it's very random. So for example, if I know I've got a height of 60 here, then in the first graph I can see that the weight is probably going to be somewhere between 40 and 90. That's quite a big range. So not much of the variance in weight is explained by my height. Whereas a strong correlation, they follow this relationship much more exactly. So I can see now in that first graph, if I've got a height of 60, my weight is probably going to be around 60, or at least between sort of 55 and 65. Much more of the variation in weight is explained by what your height is, so it's a stronger correlation. But correlation doesn't necessarily mean one is caused by the other. Consider this example. We've got a correlation between ice cream sales and the numbers of death by shark. So each one of these data points is like a year or a month or something. And in the years where there's lots of ice cream sales, there's lots of death by shark. And in the years where there's not much ice cream sales, there's not many deaths by shark. Now, clearly, one is not causing the other. What's going on here is that there's a lurking variable. We call a lurking variable or a hidden variable, which is a variable which does cause both of these things, but isn't in our data. And the lurking variable here is temperature. The higher the temperature, the more ice cream sales there are, because there's more people out enjoying the sunshine and wanting to cool off. But the higher the temperature, the more deaths by shark there are, because there's more people wanting to cool off in the sea, so there's more people in the sea for the sharks to eat. So when we have two variables that are correlated, so variable A and variable B are correlated, then there might be different types of causation going on. So either we have direct causation, A causes B, or B causes A. But determining the order, is it A causing B or B causing A, is very important. We might though have mutual causation. So both A and B cause one another. A causes B and B causes A. An example of this might be if A is the amount of money spent on the arts and B is the amount of people doing the arts. Well, the more money spent on the arts, there's more things going on for people to do, so more people are doing arts. But the more people that are doing arts, the more the government notices and think that's an important thing to spend money on. So A and B both cause one another. There's a feedback cycle there. Another type could be indirect causation. So there might be another variable which sort of sits in between A and B. A causes C and C causes B. So A doesn't necessarily cause B directly, but it causes something else which causes B. An example of this is if A is last year's sales in a shop and B is this year's sales in a shop, well, just because you sold a lot last year doesn't necessarily mean you're going to sell a lot this year. But if they are correlated, then there must be another variable C in between, which could be the shop's popularity or the amount the shop is spending on advertising. The more sales you had last year, the more money you have to spend on advertising, which means you can have more sales this year. An important one to look at, we've already looked at, is the lurking variable. So A and B are correlated because there's another variable C. C causes A and C causes B. An example of this, which happened in my life recently, over the COVID lockdown that we had, I took up running. And I really like data, so every time I went running, I recorded down my distance I was doing and the time I did. And when I analysed the data, it looked like the further distance I was doing, the faster I was running. So does this mean that I am better at long distance running and really bad at short distance running? No, not necessarily. There was a lurking variable there that wasn't recorded in my data. What was that lurking variable? My level of fitness. As my level of fitness increased, I was pushing myself to do longer distances, and as my level of fitness increased, I was pushing myself to run faster. So A and B, my distance and my time, weren't causing one another. There was another variable, my level of fitness, which was causing that, which wasn't recorded in my data set, because that's not something you can record. There may also be sort of mutually lurking variable, which is sort of a lurking variable on the other side. So A and B are correlated, but not for any reason. It's a complete coincidence, but we fail to see the coincidence because they both cause something else which we know is increasing. And finally, the A and B could be correlated just down to coincidence, no causation at all. And don't rule this out. In fact, this is probably one of the most likely cases. This is very common. I'm going to give you some anecdotes now just to really hammer in the importance of being able to recognize these types of causation. So there was a review of a fire station and they were trying to work out how do they cause less damage when they go put out fires. And they found that the more firefighters deployed to a fire, the worse the damage was. So less firefighters should be deployed because the firefighters were causing the damage at the site. And they tried to use this as reasoning of how they could reduce damage at the site. But clearly something's gone wrong here. There was a lurking variable, which is the size of the fire. The bigger the fire, the more firefighters were needed to be deployed. The bigger the fire, the more damage there was. Again, this is something which a lot of people misunderstand a lot as well. So the more police officers that are out in the street, the more arrests there are. So that must mean police officers are making people break laws. No. What's going on here is that we are mistaking breaking laws and arrests as being the same thing. The same amount of people are breaking laws, we're just getting more arrests because we're catching them. A classic example that's used when talking about correlation versus causation all the time is that cars with flames painted on them get more speeding tickets, therefore painting flames on your car makes it go faster. Now clearly this is silly, but what's going on here? There's a lurking variable here. That lurking variable is the nature of the car driver. Reckless drivers are more likely to want to paint flames on their car, and reckless drivers are going to get more speeding tickets. And another real life example, and this happened about 100 years ago, people with better health have more head lice. That was recorded when nursing and data started being used for medical purposes. People with better health have more head lice. So they used to prescribe head lice to sick people because obviously the head lice was stopping people from being sick. Now this is wrong, and it takes a bit of thinking about why. There is no lurking variable here, but we've got our causation the wrong way round. It's not that head lice were making people better. It was that sick people were killing the head lice. Sick people had a temperature, and head lice couldn't live in the heads of people who had a temperature, so they were dying, so they didn't have head lice anymore. So the causation here was actually the wrong way round. And I mentioned about complete coincidences with correlation, and this happens all the time, much more than you think. Here's a really nice website that shows lots of examples of these sort of coincidental correlations. It's called Spurious Correlations. And there's example after example of these sort of things, which is graphs of time, and over time, two variables, their trends over time are nearly exact. So in this case, if we look at the trend of the age of Miss America over the last 10 years and the number of murders by steam, hot vapours and hot objects over the last 10 years, we can see that their trends follow a nearly exact correlation to one another. Clearly these are not causing one another at all. This is complete coincidence. Would you expect this to happen though? Yes, you'd expect this sort of thing to happen all the time. And why? Think back to the law of truly large numbers. The more random trials we do, the more likely we are to see extreme things. A coincidence is an extreme thing, so the more comparisons we do, and this website does a lot of comparisons to a lot of variables, the more comparisons we do, the more likely we are to see this sort of coincidence. So this is completely expected. The last thing I want to talk about is geographic data. Care needs to be taken with geographic data because geographic data tends to contain a lot more information than we think it does. And this actually cropped up in my own work. I was looking at Gwent in South East Wales and I was comparing deprivation to number of elderly people living in an area. What I was reading from these graphs was that in the least deprived areas, so those dark blue areas, in the least deprived areas, we had more older people living there. And I tried to interpret this. I was thinking, oh, well, maybe once people have lived their lives and they retire, they like to retire to nicer places. They go to less deprived places to retire to. But that's not what's going on here at all. Actually, we're measuring the same thing. Because one of the things that the Welsh Government uses to measure deprivation levels is unemployment. And elderly people, whether they've got a job or not, do not count as unemployed because they're retired. So the places with a lot of elderly people have a lower unemployment rate because they cannot be counted as unemployed, and so have a lower deprivation rate. And a really nice example of care needing to be taken with geographic data happened right at the start of the COVID pandemic. A paper preprint came out where the authors were trying to claim that the COVID virus liked a certain climate. But what they did, they looked at a map of the world and they looked at climate, sort of temperature. So you can see from purple down to red, the different temperatures. And they circled the areas where there were big COVID outbreaks. So you can see Japan, China, Italy, France, Spain, and a bit in Washington there. And the authors thought, oh, maybe this virus likes a certain climate. Clearly we know this is wrong now, but what was going on? The virus doesn't like that green temperature area. The virus likes people, and people like that green temperature area, which is why most of the big cities in the world lies in that green temperature area. Whenever you deal with geographic data, there's usually a lot of lurking variables attached to that geographic data. When you talk about a point on a map, you're not just talking about where on the world it is. You're talking about culture, you're talking about people, you're talking about this, you're talking about that. There's a lot to unpack with geographic data. So be very careful if you think you've found some sort of correlation with geographic data.